Welcome to the course of Mechanics of Machining. Today I am going to discuss about tool wear and tool life. This is the 13th lecture in this course. What is tool wear and tool life? First, let us discuss about the wear. Wear is the failure of cutting tool due to repeated operation and loss of material from the surfaces in sliding contact. Tool is in contact with the workpiece, even the chips are sliding on the rake surface of the tool. So gradually there is a loss of material that is called wear. Wear can be caused by various reasons. Adhesion, that actually suppose the chip is flowing on the surface, it may adhere to the surface, there may be due to adhesion, and after that adhesion is a type of small welding, and then after that it is removed. So it takes some material away. Suppose there is one surface, asperity is there, this surface is not smooth, there are asperities, it may be like this. Another surface is also having these type of asperities, suppose they come in contact like this. So momentarily there is a welding, and then after that this, when they separate due to force, because there is a relative motion, then it takes away some fragments, that is basically adhesion. Abrasion is actually caused by, suppose you have some soft material and on that top of it there is some hard particle or hard material that abrades it. That means because of it something like it plows whole material, that is called abrasion. If you see the dictionary, erosion will be mentioned as one synonym of abrasion, but there is some difference, there is a fine difference, and that may differ from book to book also. But generally in erosion there may be some fluid material in that, it may get eroded. Suppose there is a rock and in that water is flowing, so we say that water is eroding that. But if there is a solid material, we say it is abrading that. These type of fine differences are there, but otherwise you can say, people generally say abrasion and erosion combine. Then surface fatigue is there, because surfaces are on contact, tool is in contact with the workpiece, there are contact forces. So suppose tool is making contact here, after that it will go away, it will separate. So the surface of the tool gets oscillating stress, because suppose when this tool is actually taking a large cut depth, then in that case large amount of forces come on the tool, but then once it has removed that material, then the force comes down also. So there is alternating or fluctuating force is there, and because of that you will get fatigue. Then there can be glass fracture. Suppose load is force is more than the strength of the material, then tool can separate. That suppose this type of tool is there, maybe it can fracture like this, this portion can totally go away. Then of course high cutting temperature. High cutting temperature takes place, that is why the tool will become soft, it will lose its hardness, hot hardness, and that is how that you can get this type of wear. So wear process generally involves more than one type of wear. One is adhesive wear particles, first formed due to welding, as I have told. Adhesive wear is very common, and then these bonds they get broken. Breaking of surface asperities may oxidize and produce harder material. That means they get broken and they get exposed, and there can be oxidation, and that oxidation, those oxides can be actually much harder. That type of thing can be there. And oxidized abrasive wear particles may act as solid lubricants sometimes. Sometimes oxidized lubricants, they may be bitter also, and they may reduce abrasive wear also. So that means wear is a very complicated phenomena. We cannot say definitely that what will be its effect. Usually we try to make assessment based on some experiments. So next Uh, so suppose discuss one by one. I am going to discuss. Suppose we discuss adhesion. In the cutting tool, three type of wears are very common: adhesion, abrasion and diffusion. Now let us discuss how the adhesion wear takes place in the cutting tool. Adhesion, you can say in one word, it is basically welding and fracture of surface asperities. Surface is not smooth. If you see under the microscope, it may be having this type of undulations. It is not smooth. Other surfaces also not smooth. And when the peaks of both the surfaces contact with high amount of pressure and temperature is also there, then there may be at micro level there may be welding. And then after that, because that welded joint is not very strong, it separates also, so it causes the fracture of surface asperities. Suppose this surface is there, another surface has come in contact here, they will weld here, but they will separate. So they will, in the process of separation, some material will be removed. Maybe some material has got removed from both sides, from this material as well as from this material. Adhesion wear may be called adhesive wear. Usually this we used in grinding. In grinding we use term adhesive wear. Dictionary meaning is wearing away by friction. In grinding, wear of abrasive grains such that sharp edges gradually become rounded, that is called adhesive. It is basically rubbing off that and grinding, the two to which we say grinding wheel becomes grazed. It looks a shining type of thing, and you will say that this is basically some grazing type of thing occurs. So you will see that because these sharp edges will become rounded, and you can identify by naked eye that the grinding wheel has become grazed. Then there is a galling. When large particles are removed, that is called galling. Removed particles may stick to other surface. Second type of wear is abrasion. Scratching materials must be at least 20% harder. Abrasion is due to scratching. Suppose I am having some type of, suppose this is wax, and on which I am moving a knife. So this knife is actually abrading the material. So here that what happens, that the scratching material must be at least 20% harder. Then it may be caused due to ploughing, cutting and fragmentation. There is a ploughing type of phenomena, it cuts also and the chips get fragmented, means when it is cutting then there will be fragmentation. Then diffusion. Atoms from one of the mating surface may get diffused into the matrix of the other surface depending upon relative affinity. So there can be diffusion. Suppose some work material is containing carbon. It is possible that this carbon may diffuse into the tool material, or vice versa. Sometimes tool is at very high temperature, from the tool that some material may diffuse into the other workpiece. So atoms from one of the mating surface may get diffused into the matrix of the other surface depending upon relative affinity. That is called diffusion wear. So in this case, adhesion wear is very common on the flank surface of the tool. You have flank face and rake face. Suppose I am making one tool in orthogonal cutting and it is cutting like that, chip is flowing here on that. So this surface is called rake surface, as you know. The rake surface is that surface on which the chip is flowing, and another surface is called flank surface, side, which is generally in touch with workpiece. That means it may rub against the workpiece. So there are two surfaces. This type of adhesion wear is more common in the flank face of this one. So when two mating surfaces come in close contact, strong bonds are formed due to welding of surface asperities. If the bonds formed at the asperity junctions are stronger than the local strength of the materials, then particles may transfer from one surface to the other when the junction fractures. So this one, so suppose I have got this thing and if I have made a bond here, another material is, this is material number 1, this may be 2. Here the bond has formed, this bond is very strong, but you applied more force because surface 2 has to move, so it will move, but since bond is very strong and below the bond this material is not that much strong, so what it may do, that some portion of this material it may fragment from here and some portion of material 1 can be removed. Means bond will also go, so that means you may have, I am showing exaggerated, you may have this situation that this 2 component has come here, this is the bond and this surface has moved, this type of material of 1 also has moved with that. So it is really a small portion of material 1. If there are 2 types of wear, adhesion wear, atresia, that means removed wear particles are very small, it is a gradual wear, and in galling the removed wear particles are large. Then about abrasion, when 2 surfaces are in sliding contact, the surface asperities of the harder material produce a series of grooves on the softer material. So that means basically this is a soft material, on that a hard material is moving like this, and this is abrading. It is like this, like this. Okay, like this. So this is making a groove. If you see, if I make the top view, you may observe this type of groove type of thing here. So the source of hard materials are scale or sand remaining during casting, because we are concerned about tool wear. So what I am telling, that surface of the tool may get abraded. Who will do that? Why? You say tool is very hard. Tool is harder than the work material, but then also the work material may have some constituents which will be very hard. For example, in a casting there may be some sand particles. These sand particles which were produced during casting, they may abrade the tool, and there may be wear particles also, they may also abrade. To have abrasive wear, it is necessary that one material is harder than the other is softer. So what may happen, that maybe very high temperature can rise. When high temperature reaches, then the tool becomes soft, relatively soft, and suppose you have this sand particle or anything, or even the material is also suppose hard material, and its temperature may not reduce that much. In fact, tool temperature may reduce more, then that particular portion can be removed. That means workpiece may contain some constituents which may be harder than the tool at that particular temperature, and it can remove this one. So abrasion wear rate depends upon the hardness, elastic properties, and the geometry of the mating surfaces. The erosive and cavitation wear are similar to the abrasive wear. Just like abrasion, in abrasion what we mean, that suppose it is one best example is there, suppose you have butter and with the knife you are removing the slice of that. So you are basically plowing. I am having this material and on that I am plowing, I am rubbing, moving. Let me make correct type of figure. Okay, here I can, okay, let me just erase this like this. See, even here I may be doing some abrasion when I am moving. So here what may happen, I have some suppose soft material and this is a tool type of thing. I'm just, so it is abrading, it is moving, it takes some cut, means it plunges a little bit, and it is hard and it is removing. So it is removing the material like this. So that is called abrasion. but sometimes suppose some water fluid is moving or some chemical is moving, so this particle may get dissolved. That is generally we call erosive wear. And cavitation wear is what? You know that cavitation sometimes occurs, particularly this is very common, not here, but suppose in turbines etc., that you have some water turbine, and suppose at some location the partial pressure becomes very low, so that water may vaporize and again it may condense, and it can condense and it can drop with a force. That phenomena is called cavitation. So cavitation is also similar and it erodes that. You know that I can have say jet of some vapor or something. So this cavitation is also similar to that. Scratching can be considered as the form of vibration wear. Suppose we scratch, we have scratcher, surface scratcher is there. So in that there is a scratcher is there, that like I am doing scratching here. So this is also a form of abrasion wear. So these wears are also there. And then diffusion wear, that is more common on the rake surface, not on the flank surface, because rake surface temperature is very high. We have discussed in the previous class that you get lot of temperature on the rake surface at some distance away from the tool cutting edge, that means from nose of the tool. So in diffusion wear, atoms from one of the mating surfaces may get diffused into the matrix of the other surfaces depending on the relative affinity of the atoms. It causes a change in physical properties such as hardness, toughness, ductility. Diffusion is a time and temperature dependent phenomena. It depends on the time of contact. More there is a contact, more will be the diffusion. Diffusion is a process which is dependent on the time, and also it is dependent on temperature. Diffusion is basically a type of chemical process when one constituent will enter into the other because of the concentration difference. So it is accelerated usually by temperature. At high temperature, more material will diffuse. So it occurs due to high interface temperature between tool and the workpiece during machining. Due to high temperature, the atoms from hard material get diffused to the softer material, and the mechanical properties, hardness, ductility and toughness get changed. So they get diffused to the, so what happens, that tool is suppose very hard, but it is hot, and from there it may get diffused into the workpiece, and therefore tool may become weak. That type of thing may happen. Now, so progressive tool wear, what do we mean by progressive tool wear? That means wear is increasing with time. So I have made a schematic diagram here. This is the workpiece and this is a cutting tool, and this is doing cutting. Suppose workpiece is coming in this direction. So material is removed in the form of the chips. As you can see that the chip is rubbing against the rake surface, and maximum temperature may be somewhere here on this surface, in this one. So two type of wears are very common. One is the flank wear. On the flank surface, this material, some wear may take place, and therefore this is the wear land. Maybe this much material gets removed, ultimately this portion comes. So flank wear will affect the dimension, because as you can see that suppose this portion has come in contact, and therefore that what happens, that instead of this much surface, now this one is there. So it is basically effectively that distance from this one has increased. Suppose here you are getting this type of surface, but suppose this material has been removed. So now the tool's location is here, this one. So this nose basically has shifted from here to here, because that much, so new geometry is this, because the bottom portion has worn out. So that means effectively now Earlier the depth of cut was from here to here. Now the depth of cut is from only here to here. So that means you basically get dimension. So dimension stability is affected by means of Frank wear, and this much material has been removed from here to here, and this portion has come in contact now. So this is called wear rand. LW is the wear rand. On the other hand, crater wear takes place on the rake surface. Here you get a crater type of thing, that means a pit type of thing, like this type of pit, some material. So crater wear occurs here. Crater wear will not affect the dimensional stability because crater is on this surface, but dimensional accuracy is affected by this one. But crater may change effective rake angle and it generally makes the tool very weak. Suppose this much crater has been created, so you see that here this much material is only left. So the tool has become very weak. So frank wear is the wear taking place on the frank face of the tool, and crater wear is the wear taking place on the rake face of the tool, like crater or pit. This is called crater wear. Frank wear is usually evaluated in terms of the length of the wear rand, which can be measured by means of a measuring microscope. We can see it on a tool maker's microscope. So this is frank wear rand from here to here, if you say material has been removed. And wear rand growth can be divided into three regions. We can make time versus frank wear. So initially the wear is very rapid. Why? Because on the surface there may be already some asperities which are actually very high, maybe 1 or 2 and in an irregular way. So what will happen? That they will get worn soon. But once they have become worn, then more or less you get relatively flat structure. So now the wear will be small. So initially there is some break-in period in which the wear rate is very fast. Then there will be steady wear zone which is for a longer duration, and after some time the tool will become very weak, and then there will be severe wear zone that will be very rapidly causing tool to fail. So initial wear zone, that means sharp cutting edge of the tool is quickly broken down. Suppose tool is there, it is having very sharp cutting edge in beginning, then it will produce large amount of stress also, because the stress is force divided by area. So that sharp cutting edge will experience lot of stress, and it will be getting broken or fractured, or it will deform here. Then what happens, that remaining, suppose this much small portion gets, so it automatically will become rounded type of thing, and contact area will increase. So now further wear will reduce. So in the beginning, sharp cutting edge of the tool is quickly broken down, and wear rate in this region is high since the area of contact is less. That is the initial tool wear zone. This figure is not to the scale. Actually this region may be very, very small, and this region can be very big, actually middle region. Then we have got steady wear zone. In that experiments show that normal force on the cutting tool is proportional to the size of wear rand. So it is generally proportional to the normal force, and rand growth curve is usually linear, and wear increases at a uniform rate. Then we have got severe wear zone. That means wear rate is high because of high temperature plastic deformation. When lot of wear has taken place, more wear has taken place, more area is in contact. Suppose even the tool was very nicely doing its job in the beginning, and it was having something like this type of shape, not much portion was in contact, but after some time when the material has worn, then there will be more contact. Just like suppose you have got, suppose some tire, it is a brand new tire, it will be having contact at a point, and then after that suppose tire gets worn out, then it will be more surfaces will be coming in contact, and therefore this temperature will increase further, and high temperature you will be getting, and then the wear rate will be very rapid in this case. So finally that wear rate is very high, and generally it is seen that the wear band is proportional to FQ, particularly in steady wear zone. So FQ is maybe the force, normal force coming on the tool. We did some experiments actually with time and wear. We are measuring the wear up to now. We have taken one condition in which cutting speed was 135 meter per minute. These were carbide tools. Feed was 0.32 mm per revolution. Depth of cut was 0.3 mm. And we got this type of curve. See, we have got very small here, the wear is very rapid, but then more or less it is steady. Wear rate is not very high, and we did only up to this. We got a wear of about less than 0.18 or something. But here the second case, you have velocity cutting speed of 270 meter per minute, feed of 0.32 meter per revolution, and depth of cut was 1.2. So more severe conditions. So here the wear rate was very high, very rapid, and you are having that here, you see up to that about, I think more than 0.6 or something like 0.6, up to 0.6 or 0.7, that you just see. No, if you draw maybe 0.6 is up to here only, and this may be 0.7. So between 0.6 to 0.7, somewhere that much wear has taken place, and naturally the tool is considered to be fail. Many people take this as a criteria that this much amount of wear band I will tolerate. If the wear band is beyond that, then naturally it has to be, tool has to be changed. So I just showed these two figures to illustrate that how the cutting conditions affect the flank wear. Now what about crater wear? Crater wear is evaluated in terms of the depth of crater, and the shape is assumed to be segment of an arc. That means basically it is usually will occur on the rake surface of the tool. Suppose this is the tool, this is nose and this is rake surface, and here I get a crater type of thing. I got a crater this much. That means this is, you have got a crater. Let me erase that upper portion. Yes, up to this. That means now the tool has become like this. We got a crater type of thing. Just like we get a pit in the road, pothole type of thing. We get that type of crater we will be getting, and it is evaluated in terms of the depth of crater. That means we say how much is the depth of the crater from here to here, and the shape is assumed to be circular. At low cutting speed, the cutting is protected from the action of the chip because of the formation of a stable built-up edge. At low cutting edge speed, already there is built-up edge, so chip will slide on the top of the built-up edge, and there may not be contact of the chip with the rake surface, so we don't get a crater. But at high cutting speed, diffusion plays a major role. Why? Because at high cutting speed, temperature also becomes high, because more power is there that gets converted into heat. So maximum temperature at the chip tool interface appears to exist at some distance from the tool edge, not at the tool edge. Maximum temperature is not here, rather it is here. Why it is here? Because already some heating was done because of the plastic work. Then on top of that, chip is sliding, and the chip is sliding, so its temperature is again increasing. So it may be somewhere here, maximum temperature. That is why maximum amount of crater wear is here. At higher speed, the crater wear is predominant than flank wear because diffusion is a temperature sensitive phenomena. It occurs at high velocity tool chip interface. So generally it will occur on this one. Now, having talked about the flank wear and crater wear, which are the two common wear, in which, of course, as I told, dimensional stability or dimensional accuracy is affected by flank wear, and rake angle is affected by top rake angle by crater wear. Even side rake angle also will be affected by crater wear. So, tool life we should discuss now. A tool life is what? A tool that no longer performs the desired function is said to have failed. That means we say tool has failed. Tool life can be defined in many ways. One is cutting time to failure. Like after 5 minutes of machining, my tool failed. Then we say that tool life is 5 minutes. Cutting length to failure, that how much meter it has moved. So that means cutting length. Or volume of material removed to failure. That means before failing, how much volume it has removed. And the number of components produced to failure. We can do like that. If there are similar type of components, we can say this tool made about 100 components, other tool made 150. So one tool's life is 100 piece, others is 150 piece. But cutting time to failure is most common tool life. Various ways in which tool failure can be identified. First, we have some criteria about wear and size. Say for example, we say HSS tool is there, and we say if the wear band is more than 0.4 mm, then we will say tool has failed and we will change the tool. So wear band size is there, depth of crater can be there, some criteria, tool wear volume we can measure, magnitude of cutting forces. That means we can also say tool life like this, that if the cutting forces will increase, then we will say the tool life is over. When the tool life will be over, the forces will increase to a large extent. Then surface finish value, suppose we are not now getting the good surface finish. In the beginning surface finish was good, but now the surface finish has become poor. Then also this one, change in component size. Suppose lot of flank wear is there, you are doing the same type of setting, but now you see that your component is of slightly increased size. That means some wear has taken place. And total destruction of the tool, sometime catastrophic failure can also be there. That means tool can get broken. Variables affecting tool life are cutting conditions. What is the feed, depth of cut and cutting speed. Tool geometry is one feature. Then tool material, and then the work material, and whether we are using cutting fluid or not. Because cutting fluid does some lubrication, so maybe the tool life will improve. Cutting condition means experimentally it is found that the rate of wear increases as cutting speed is increased. The wear and cutting time curves are obtained at various cutting speeds. Suppose this is the at V1 is less cutting speed, V2 is more, V3 is the highest cutting speed in this figure, and this is the wear and this is cutting time. So we are seeing that here at low cutting speed, first you are having some initial wear period, then steady wear period, and then high wear period, rapid wear period. But this wear is nevertheless less. If the cutting speed is increasing, then the wear is increasing, and similarly if the cutting speed has increased further, then wear rate has increased further, and overall life has reduced. From such curves we obtain tool life at various cutting speeds. For the critical wear and size LW can be obtained. I may have some criteria. So my critical wear may be LW star. When LW star wear will take place, I will stop my machining operation and change the tool. So you see that LW line was cutting this curve here at this point. So at V1 the tool life is T1, at V2 the tool life is T2, and at V3 the tool life is T3. Taylor did this type of experiments basically in the last decades of this one 19th century, that means before something like 1900, and he has done lot of experiments, F.W. Taylor, and he machined several means materials and got lot of data, and that he has, in fact he has tons of material, I think he machined. So he gave, and this study he conducted for about a decade, and then he obtained this type of Taylor tool life equation, that is Vt to the power n is equal to c, where V is cutting speed, T is tool life, n and c are constants. So V is cutting speed, T is tool life, and n and c are constant, which depend on the tool and workpiece combination. So this is called Taylor's tool life equation. I can plot it on log plot. I take plot here log V and log n, then I am getting a linear type of curve, and the slope of this one is basically 1 by n, means tan theta is equal to basically minus 1 by n. So this we can find out. If we can conduct a lot of experiments, we can plot this type of curve, then we can find out exponents also. So this equation one can use. The variables speed, feed and depth of cut affect the material removal rate and hence have direct bearing on the production cost. The above equation can be rewritten to show the effect of cutting speed as tool T is equal to C1 to the power n divided by V1 by n. So you can see that if n is very small, then we will have more effect, much more effect on that one. But suppose n is very large, then it may not have that much effect. So tool life can also be expressed as T is equal to C1, V1 by N1, F1 by N1 and D1 by N1, or sometimes we say V and maybe F to the power something X and D to the power Y and T to the power N is equal to constant, this type of thing. No matter in what way you express, here it has been expressed in this way, T is equal to C1 by this one, but or you can express in this way, but this is called Taylor's extended tool life equation. It is showing the effect of F and D also. If F increases, then also tool life decreases. If D increases, then also T tool life decreases, but effect of the speed is more. That means in this expression 1 by n is much more than 1 by n1 and it is much more than 1 by n2. So it indicates that the cutting speed has greatest influence on tool life, followed by feed and then depth of cut. So therefore what you should do, that you should try to take as much depth as possible and then you can have more feed also, but try to have the cutting speed somewhat small. Now tool life is related to cutting temperature irrespective of the cutting condition, means whatever effect is there, cutting speed's effect or feed's effect ultimately generates some temperature, and we can also write this type of equation that T theta m to the power m is equal to C2. In general, the cutting temperature will increase with V, F and D, and hence the effect of these variables can be combined in terms of temperature. Now let us see that what is the effect of the tool geometry. Rake angle, what is the effect of the rake angle? If we increase the rake angle, then the cutting force reduces and the cutting temperature also reduced because of that, so it results in increased tool life. But when the tool rake angle is very large, although the cutting forces are lower, the tool edge is weakened, resulting in increased failure to chipping off the cutting edge. So that is why that if the rake angle in the, suppose there is a tool like this, its rake angle is this, if I increase the rake angle, that means this surface really has come here, then in that case you see the tool has become weak. Earlier this much thickness was there here, now this thickness is this much only. So that is why tool edge will be weakened and it will result in increased failure to chipping off the cutting edge. Hence there is an optimum rake angle which gives the maximum tool life. So that is why you are seeing that the tool life is first increasing with rake angle and then it starts decreasing. So there is an optimum rake angle. Same thing happens about flank angle or clearance angle. Here that cutting tool is there and this is the flank surface. This is the surface which is machined. There is some gap between machined surface and this. Now if I have it very less, then there will be rubbing between the workpiece and tool. There may be some, even if we set it like that, there is a clearance here, but because of the heating, there will be expansion. So this portion will start touching the tool here. These type of, so therefore you have to have sufficient gap. So there will be rubbing between the tool and the workpiece, and hence if you increase the flank angle, then it will reduce the rubbing between the tool and the workpiece, and hence it will improve the tool life. But again, if you increase the flank angle too much, again tool gets weakened, because suppose I am showing that suppose this is like this. Now you want to increase this one flank angle, then you may make a tool like this, but this tool is thinner. So optimum value of flank angle is also affected by the feed rate. Higher the feed rate, lower is the optimum value. So here it is this one, here the optimum flank angle here is this, but if the here F1 is more, much more, and this is less, so that is what it is happening, F1, F2, F3. Yeah, F1 is the highest, so you are having optimum flank angle is less. Side cutting edge angle, for a given feed and depth of cut, the length of the engaged cutting edge increases with increase in the side cutting edge angle. This gives lower cutting temperature and hence increases the tool life. So side cutting edge is also having this type of behavior. And nose radius. Nose radius on the tool is favorable for long tool life. Suppose nominally sharp tool is highly stressed at the tip and has sharp tool life. Increase in nose radius improves the tool life. Increase in nose radius also increases the cutting forces and is conducive to chattel. So therefore you have to have here also some optimum nose radius, and that is generally kept between 0.5 to 2.5 mm. These type of we keep. Now what are the properties of the tool materials? Very important is the hot hardness. That means it should retain its hardness at high temperature. Then it should be tough. That means it should be able to withstand shock and fracture. It should have high resistance to wearing action. It should have coefficient of friction should be low. Its thermal conductivity and specific heat should be high. Thermal expansion should be low. It should be easy to fabricate and cheap in cost. Wide variety of cutting tool materials are still used, and the common ones are carbon tool steel, basically high carbon tool steel, then high speed steel, then cast non-ferrous alloys, then cemented carbide, sintered oxide, and artificial abrasives. We can have diamond also. Carbon tool steels will contain generally carbon in the range of 0.9 to 1.2% and some alloying element. It may have manganese and this one, small amount of sulfur is also there, but not much used in industry nowadays. High speed steel, usually they contain suppose 18% tungsten, 4% chromium and 1% vanadium. This type of steel is called 1841, and there is some carbon and manganese is also there. Molybdenum HSS is basically tungsten is replaced by molybdenum. So we have 8% molybdenum, 4% chromium, 1.5% tungsten, 0.6% Mn and 1% vanadium. Super HSS, super high speed steel, 12% cobalt is added to better hot hardness and resistance to abrasion with some sacrifice in toughness. Cast non-ferrous alloy can be 43 to 48% carbon, 17 to 19% tungsten, 30 to 35% chromium, and about 2% carbon. Cemented carbides or sintered carbides are very much in use. They are composed of hard metallic carbides like tungsten carbides bonded together in a metallic matrix. Main ingredients in most common cemented carbide tools are tungsten carbide and cobalt binder. Sometimes titanium or tantalum carbides are added to reduce crater wear. Sintered alumina containing about 90% sintered aluminum oxide plus boron nitride power. Union Carbide developed some Yukon. It consists of 50% chromium, 30% titanium and 20% tungsten and permits 60% increase in cutting speed. Cubic boron nitride, expensive tool, but it has 5 times more tool life than carbides. Hardness is next to diamond, generally used for grinding purpose. Artificial abrasives and diamonds are used. Then coated carbide are there, in which we put a thin film of TiC or titanium nitride on cemented carbide tool. So coated carbides are used for countering crater formation. A thin film of about 0.005 mm, that means 5 micron of TiC, when deposited on cemented carbide tools, reduces crater formation. Other coatings are Al2O3 and TiN. TiC and Al2O3 provide chemically stable layer between chip and tool. TiN provides low tool friction. Multi-layer coatings of TiC and TiN have been used. In this arrangement, the stable diffusion barrier is provided by TiC, and then TiN provides low chip tool interface friction. So what happens that suppose the coating I will do like this, that here suppose this is my tool, this is the rake surface. So here first I will coat TiC, and on top of that I will coat this one will be, this is not up to the scale, but I am just showing TiN. So TiN portion will come in contact with the chip, whereas TiC portion is in contact with the this side. So this is what this type of thing you can do. And the most desirable property of a tool material for machining purpose appears to be high hot hardness. An increase in hardness decreases the toughness, and we see the graph that with temperature the hardness is decreasing. So high speed steel are good about 600 degrees centigrade up to that. So these type of various type of tool materials, these graphs have been plotted. And then it has been found experimentally that the value of exponent n in Taylor's tool life equation is higher for harder tool material. That means Vtn is equal to constant in this one. And then generally that hardness of the material also affects the tool wear. That means corresponding cutting speed for a given tool life will reduce if the hardness is more. So we can have such this type of some equation, approximate equation. Cutting fluids are used for decreasing the cutting temperature and the chip tool interface friction. They also cool the workpiece to avoid thermal expansion, and they promote easy handling. They provide a rust-proof layer of the finished surface and remove chips from the machining area. Cutting fluids are either oil-based or they are water-based. Oil-based fluids are generally effective in reducing friction in low-speed cutting operation, such as typing and broaching, etc. Now, mode of lubrication is one of boundary lubrication, and the chemical property of the cutting fluid is more important than physical properties. At high cutting speed, oil-based cutting fluids are ineffective, and it is the cooling action that is operative. Water-based fluids are therefore more effective at high cutting speed because of their high specific heat and conductivity, because they have to quickly dissipate heat. Now, let us see that how we determine tool life equation. One way is that you conduct large amount of experiments at different temperature, different cutting speed, and then you can plot. But what happens, in order to evaluate tool life constant n and c of equation, cutting tests are carried out, but you cannot afford to waste a lot of material in conducting the test. So some efficient ways have to be found out. Tool life curves for the critical wear and size can be obtained and plotted on logarithmic coordinate to obtain the values of n and c graphically. An exponent can be evaluated from this relationship also. N is equal to log Vb by Va, log Tb, Ta by Tb, where Va and Vb are any two cutting speed and Ta and Tb are corresponding tool life values. We can do that, and experiments have indicated for HSS we got 0.1 to 0.15, cast hill wise N was 0.15 to 0.2, cemented carbide it was 0.2 to 0.5, sintered oxide it was 0.5 to 0.8. Now quick tool estimation methods are like that. One method is based on facing test, other is taper turning test, and the third is the disc turning test. In facing test, what we do, tool traverses radially outward from diameter D1 to D2, thereby changing the cutting speed continuously from V1 to V2. So cutting speed is continuously changing, it is not a constant speed. I will put a tool here and the tool will start moving like this. So it will do facing, you know facing operation. Hai na? If I show the other view, it is a circle and this face will be machined. So effect of variable speed is evaluated in terms of equivalent cutting speed, which is constant speed and give the same tool wear in the same cutting time as the variable speed. You assume their linear wear and growth because steady wear zone, you have seen that wear and is proportional to time. So we say dLw by dt is equal to Frank wear and L star W by tool life. This equation is there, you can use, and then we conduct tool life testing like this, wear and size Lw and criteria for Frank wear and this is what you see that it is linear. So here, if Taylor tool life equation is assumed to hold in the range of cutting speed covered while the tool traverses from diameter D1 to D2, D2 is more than D1, the wear and Lw1 at any time T1 can be obtained by this formula, Lw1 0 to T1, and we have Lw Cn Vn dt. Since equivalent speed Veq will also give the same Frank wear and after time T1, then we get this type of relation. Lw1 is actually this. So if we make the correspondence between these two, we get V equivalent is equal to 1 by T1, 0 to T1, V to the power 1 by n dt to the power n, and we are getting this type of relation. If Taylor tool life equation is assumed to hold in the range of cutting speeds covered while tool traverses from diameter D1 to D2, the wear and Lw1 at any time can be obtained like that, 0 to Lw1 TL is equal to 0 to T1 beta Tt dt, where beta is the slope and the constant slope is estimated from this. So we get Lw1 is equal to this one, and at L is equal to Lw star, T star is equal to this much, and slope beta is L star W by T star, that can be written as L star W star by Taylor's tool life equation, Vtn equal to constant. So T star can be written like this and you get this equation. So corresponding equivalent speed comes out to be this one. Since equivalent speed will also give the same Frank wear and Lw1 after time T1, so we get Lw1 is equal to this much, and then if you equate in facing test the cutting speed varies with diameter and time, as this one V is equal to 2 pi Rn, R is the radius and 2 pi n, and this is Fnt plus R1. F is the feet per revolution, and this one. So here equivalent speed in facing from radius R1 to R2 in time t can be obtained by putting these values and integrating then you will get equivalent speed and you get T1 is equal to this much, R2 minus R1, D2 minus D1 by this one. So you can obtain this one for a given D1 and D2, V equivalent is proportional to N, and the effect of cutting speed on tool life can be obtained by varying N. So fraction of tool life consumed in time T1 when tool moves from D1 to D2 is X is equal to this much, and X is equal to pi N by C, and this one you can substitute these values. Equivalent speed LW1 is equal to this much. This is also given here. If X1 and X2 are the fractions of the tool life consumed at spindle speed N1 and N2 for a given D1, D2 and F, then X1 by X2 is equal to this much. So if we put these things, ultimately we can get N is equal to in this form and C is equal to this much. So performing tests at two different speeds N1 and N2 and diameter D1 and D2, we can obtain C and N. In the same way, we can do taper turning also. In taper turning, the tool is experiencing the variable speed because change of diameter. In this case, the equivalent speed expression becomes this, and fraction of tool life consumed comes out to be like this. There is some algebra which I am skipping here. Now, by performing two taper turning tests at spindle speeds N1 and N2, the corresponding values of X1, X2 can be obtained, and again you can obtain and N can be evaluated using that type of equation. And so they have obtained that, suppose taper turning test, somebody obtained this type of curve, and by conventional turning also the same type of curve, similar type of thing was obtained. In disc turning test, it is done in the same way, but here we do the machining of a disc basically. So we get this type of expression. Instead of we have a disc not facing, it is a hollow type of disc that we are basically machining. So we are having this type of expression, and fraction of tool life is this. So in these equations, D1 is greater than D2, and in facing test D2 is greater than D1 since the tool moves outwards. But in this one, we are machining basically the disc, and from D1 to D2. So that means here we are doing turning. Disc is getting turned, and then we can be, it can be obtained that here we get a similar type of expression, and we can also get this one. Now last point is that machinability. What do we call machinability? Criteria used in these attempts could be classified into the following four broad categories. Tool life criteria, based on the tool life. Suppose tool life in machining a material is better, then we can say the machinability of that material is better. Production rate criteria, if the production rate is high, machinability is good. Power consumption criteria, if power consumption is less, then machinability is good. Surface finish criteria, if the surface finish is good, we say machinability is good. So when tool life criteria used, it is common to express it in terms of the cutting speed for a given tool life. We can have some reference. For example, if VTS is the cutting speed for a tool life of T minute for the standard material, and VTM is the cutting speed for the same tool life for the test material, then the machinability of the test material can be expressed as VTM by VTS into 100%. Suppose the cutting speed while machining material is same as the standard material, machinability is 100%. If the cutting speed is much more, then the machinability is more than 100. So like that. Otherwise it may be less than 100%. So these things are there. The expressions for variable tool life machining, variable tool speed, for finding out the cutting tool life, okay, you can easily nicely do, because there was a lot of mathematics. Maybe you might have faced some difficulty because I have not derived very slowly, but this if you see that this book, you can easily understand these expressions. in the book of GK Rao, and you can just do simple arithmetic and you can get to do that. So I have told you today about the tool wear, in which I told that crater wear and flank wear is important, and tool life also we discussed about tool life. Usually Taylor's tool life is very an empirical way to estimate the tool life, and then I talked about the machinability of material. Suppose you can cut the brass very easily, then it is called brass is has got a good machinability. If you cannot cut some material very easily, it has got poor machinability, and machinability is can be assessed, means cutting easily means the force should be less, surface finish should be good, and tool wear should be less. So any of these criteria or a combination of so many criteria can be used, and then you can define machinability. In fact, definition of machinability may vary from context to context and person to person. It is basically a subjective measure, and this one. So in the next class we will discuss some more interesting things. Okay, thank you.